All right, welcome back. So this is an ALEKS topic that's called using the ideal equation of state. And there's a lot of different versions of this topic, and a lot of them are a lot easier than this one. So most of the ones that you're going to run into, they're fairly straightforward. You know, you've got PV equals nRT, you've got 3 out of the 4 things, and you sort of need to apply it. This problem is much more involved, and this is sort of the hardest version, I guess, that you would run into. And there's a lot of different conversions and things that we need to take into account. So let's go and get started. So in this problem, we're told, this is more like a real world situation. We have a stainless steel cylinder. We've got the the width and the height of that cylinder. So from this, we could calculate the radius. We're going to need that for the volume. And it tells us the maximum safe pressure inside the vessel has been measured to be 7.6 megapascals. So what I did first when I was looking at this problem or doing this problem is I just Googled for the volume of a cylinder because that's not something that I had off the top of my head. And I found that it was pi r squared h. So the next thing that I did is I said, okay, well, what would be the volume in centimeters cubed? Just because I'm given centimeters. Ultimately, we're going to want to use liters for the ideal gas law. But initially, we could just sort of say, well, what am I given? Let's just use that. So if you plug in pi 24 centimeters, so this is my width, but I want the radius, so that's going to be half of your width, 24 centimeters squared, times the height, 57.6 centimeters. Then your volume that you're going to calculate here, which is 104,231 centimeters cubed, right, is going to be in centimeters cubed. So then what I did is I said, well, what's the conversion between 1 liter and centimeters cubed? And I found that 1 liter, you might know that centimeters cubed is a milliliter. So then we would know that 1 liter is 1,000 centimeters cubed. And I could go ahead and convert this times 1 liter over 1,000 centimeters cubed equals 104.2 liters. So that's step one. That's the first thing that I did. And I haven't even finished reading the question yet, but I'm already sort of going through, breaking down what's the information that's given, how can I sort of treat that to figure out what the volume of my cylinder is. So now I've got a volume in liters, which is ideal for the ideal gas law. The next thing I did is I took this 7.6 megapascals and I literally just typed in 7.6 megapascals, 2 atmospheres into Google, and it told me that it was 75.0 atmospheres. And I think that when you're doing this ALEKS stuff, I think that that's totally fine, right? This problem, it does have us do a lot of conversions, and there's a time and a place for that. But I think if you're just trying to make sure that you get make sure you have the right information, just Google 7.6 megapascals, 2 atmospheres. This is something that I feel totally fine with. Okay, so now I've got a volume and I've got a pressure. So that maybe we'll put equals pressure, right? This equals volume. So now I'm going to read the rest of the question. For a certain reaction, the vessel may contain up to 17.1 kilograms of sulfur tetrafluoride. So 17.1 kilograms equals 17,100 grams of sulfur tetrafluoride, SF4. So I'm going to convert that into moles. So 1 mole should equal 108.07 grams. So just finding the molar mass of SF4. And that equals 158.2 moles of gas, SF4. So that would be the number of moles that we're going to be putting in, the number of moles of gas molecules that'll be moving around. So this is just another piece of information. So then finally it says calculate the maximum safe operating temperature. So what we're looking for is a temperature the engineer should recommend for this reaction. So if we think about PV equals nRT, obviously we're going to be using this equation, ideal equation of state. I know my pressure, I know my volume, I know my number of moles, R is a constant, so I can solve for this temperature here. So really, this problem is just sort of a long way to get to, let's use the ideal gas law, but we need to do some conversions and we need to think about, well, what are the sort of real world type calculations you might have to do if you were a chemical engineer or if you were working in industry. Okay, so anyhow, 75.0 atmospheres for my pressure, 104.2 liters for my volume. My number of moles is this 158.2. R value 0.08206. Make sure everything's fitting on here. And we're solving for T in terms of Kelvin. So go ahead and solve this for T. Keep in mind, your units are very important. Obviously, it's asking us for our temperature in degrees Celsius. So we've got 602 Kelvin. We're going to subtract 273, and we should end up with 329 degrees Celsius. So that is our final answer. Sort of working backwards, we're going to take this 329 degrees Celsius. You could plug that into your ideal gas law, right? Converting to Kelvin, obviously. But that's going to be, if you are under these, if you have 158.2 moles of gas, this is your volume, you could heat your system up to that temperature until the pressure is 75, atmospheres. If you continue heating, right, if this goes above 602 degrees Kelvin or 602 Kelvin, then the pressure is going to be, further increasing. Our volume and our number of moles are going to stay the same, but as you increase this temperature even more, then you're going to exceed the pressure, safety for that vessel. So yeah, hopefully that's helpful. I know it's a lot, but really it's just sort of a lot of unit conversions, figuring out what the volume is, figuring out what the pressure is, and then the actual calculation that we're doing is fairly straightforward. All right, hope that helps. Let me know if you've got any other questions. Cheers.